Alright, so I want to begin by giving you some information from Chapter 2 on airflow and airspeed measurement. First, we'll start with the properties of the atmosphere. If we look at the atmosphere, just for your information, it's made up of 78% nitrogen, 21% oxygen, and 1% of other chemicals. Why the atmosphere is important: aerodynamics is going to be affected by static pressure, temperature, density, and viscosity. Sorry, the pen here doesn't work too well on the iPad sometimes, so bear with me as we go through this. Pressure ratio is always going to be based on 29.92, so this is your standard pressure for standard atmospheric conditions. And most of the time you'll see this used a lot in aerodynamics, especially when we're doing computations, because it makes it easier to do the mathematical computations when we're using 29.92. If you look on page 18, you're going to see some more information about density ratios, temperature ratios. Again, the importance of this and why we use ratios is to get rid of the units. So for example, if we look at, let's take one, pressure ratio is equal to 0.6877, and if you went to table 2.1 on page 20 and you find 0.6887, you'll read a pressure altitude of 10,000 feet. So that's how you use the table. And same, if we look at another one, say we had a density ratio, it's going to work the same as pressure equal to 0.6292, and we want to know what the pressure altitude, looking at the table on page 20, it's going to be 15,000 feet. Alright, and density altitude is important because the density altitude is going to affect our aircraft performance. Now let's look at the continuity equation. This is pretty basic if you've seen this before, but basically the continuity equation states that mass airflow is a constant, and if we assume mass airflow is a constant, draw a sectional of a pipe, and this is station 1, station 2, and station 3. We can say that the density at station 1, the area at station 1, and the velocity at station 1 is equal to the same at station 2 and is equal to station 3, which is constant. And that's your continuity equation. And this is important because we're going to talk about Bernoulli and airspeed measurement here in a second. And this is on page 21. Alright, page 22, they give you the equation for dynamic pressure, and what's going to happen, what basically Bernoulli is saying is that as we pass through this pipe in this section, velocity is going to increase and pressure, static pressure, is going to decrease. This station, entrance station, is going to be equal to the exit station at station 3. So in this area it's important to compute dynamic pressure, which is going to be equal to 1/2 rho being density v squared. And if you look at the equation 2.1111, is it 2.1111? No, I'm sorry, 2.10. They write dynamic pressure this way: density ratio of velocity squared in knots divided by 295. So the reason to write dynamic pressure this way is so that you can use knots in this equation. So if I knew what the density ratio was, so we wanted to compute this, let's say at 10,000 feet using table 2.1 on page 20, 10,000 feet would give me a density ratio of 0.7385. So it would be 0.7385. Let's say we're doing 300 knots divided by 2. Divided by 295. Let me do that calculation right quick on my calculator. So 0.7385 times 300 divided by 295 is 0.751. I believe that's pounds square foot. Yep. 0.751 would be the dynamic pressure at 300 knots at 10,000 feet. Okay? So that's how you could use and find dynamic pressure. So if we draw an airfoil, it's going to be very similar to what we just explained with the Bernoulli equation. The velocity here is 100 knots. The velocity here is also 100 knots. But the velocity here is going to be 200 knots. The pressure here will be 2,116. The pressure here will be 2,116. But the pressure here is going to be 2,014. So as air flows over a wing, velocity is going to increase, pressure is going to decrease, and this is how we generate lift over an airfoil. Alright. Airspeed measurement, you can see the stagnation point. So stagnation point on page 23, this is where static pressure, the static pressure is going to be equal to the total pressure of the airstream. But since the air velocity at this point is 0, the dynamic pressure is also 0 at that stagnation point. So if we draw a simple, and I'm going to draw a simpler pitot-static system than what they have there. So trying to draw the system here. So if we draw a simple pitot-static system, this is going to be total pressure. And this is going to be, in this area, your static port. That's why we have an opening here. This is your airspeed indicator. So the pressure indicated by gauge is difference total static pressure. So your difference in the total minus the static is going to be equal to the dynamic pressure. And this is how we get airspeed. So if you look at the equation for Bernoulli, Bernoulli says that total pressure is equal to static pressure plus dynamic pressure, and we know that we just saw this equation written before. Total pressure is equal to static pressure plus density ratio knots squared divided by 295. Alright. Finally, if we talk about the types of airspeed, you probably have seen this before. We have indicated airspeed, calibrated airspeed, equivalent airspeed, and true airspeed. Indicated airspeed is equal to the pitot-static airspeed reading as installed on the airplane without correction. And your calibrated airspeed, it results from correcting for those indicated airspeed errors. So at the diaphragm, reading of the airspeed dial is where you're going to see the indicated airspeed. And if there are any errors in the instrument, this will be shown on an instrument error card, normally located at the near the instrument. And calibrated airspeed is really important when we start talking about fast, high-altitude aircraft, because the pitot tube is subjected to what's called ram effect, and it causes the diaphragm in picture 2.5 to be deflected too far. So therefore it's too high and it must be corrected, and that's the importance of calibrated airspeed. Equivalent airspeed is further correction to make so we can find true airspeed. That's really the importance of equivalent airspeed, is we're not going to see it much. It's really for us to get true airspeed, and true airspeed is equal to equivalent airspeed and the square root of density at sea level divided by the density, actual air density at your altitude. So if you wanted to calculate true airspeed, be equal to whatever your 200 knots and the square root of density at sea level, which you get from the table, divided by actual air density. All right, I think that's it for Chapter 2. Thanks for listening.